The ability to test the hypothesis that a given sample has been drawn from a normally distributed population is important in a wide range of statistics and data science applications. For example, the student t-test and ANOVA tests are premised on this assumption, and in data science, if prediction errors are not normally distributed, it often means that we can improve predictions by taking the distribution of errors into account. This presentation gives a brief overview of my capstone project, which proposes a formal normality test based on the RMSE associated with a QQ plot. Since the QQ plot is often used on its own as an informal visual normality test, the test proposed has the potential to augment the QQ plot in this use case. First, we'll briefly consider how the normality assumption can lead to an informative RMSE statistic associated with a sample of data. We'll then explore the sampling distribution of this statistic under the normality hypothesis. It turns out that the sampling distribution is well modeled by the log-normal distribution, which we discuss next. We then consider how we can assess the RMSE test proposed using statistical power as a criterion. And we conclude with a comparison between the RMSE test and existing normality tests over a range of contexts. So, what is the RMSE statistic associated with a sample of data, and how is it calculated? Here is an arbitrary sample of sorted data drawn from an unknown population. The question we are interested in is, does this sample present enough evidence for us to reject the hypothesis that the population from which it was drawn is normally distributed? The first step in applying the proposed test is to map each value in the sample to its associated z-score. This is simply the number of standard deviations each value lies from the mean of the sample, and serves to remove any units in the data. In other words, we simply subtract the arithmetic mean from each value and divide that by the standard deviation. Notice the n-1 denominator in the standard deviation formula, which addresses bias in using the sample standard deviation to estimate the population standard deviation. This slide shows our example data with each value's associated z-score. For example, the first value in the sample lies around 0.9 standard deviations below the mean, and the last value in the sample lies around 2.06 standard deviations above the mean. Notice that so far we have not made any assumptions about the underlying population. These z-scores are obtained directly from the values in the sample. If we do assume that the underlying population is normally distributed, however, we are able to associate a z-score with each value in the sample in an alternative way, which we discuss next. What we do is spread out the sorted values in the sample evenly and then center the values over a probability of 1, as shown here. In this example, there are 15 values in the sample, which means that each of the 14 gaps between the values represents a 15th of the probability. And since the values are centered, half of the remaining 15th lies before and after the first and last value, as shown here. So here is where the normality assumption comes in. Here is the probability density plot of the standard normal distribution. It is symmetrically centered about 0, has a bell shape, and contains all real numbers in its domain. The associated cumulative probability function, often written as phi, returns the cumulative probability bound by a given z-score. The inverse cumulative probability function then returns the z-score bounding a given cumulative probability. So returning to the example, we can now use the cumulative proportion associated with each value in the sample along with the inverse normal cumulative probability function to associate a z-score we would expect if the underlying population is normally distributed with each value in the sample. For example, the z-score we would expect under this hypothesis for the first value in the sample is the inverse cumulative probability given proportion 1/30. The z-score we would expect for the second value is the inverse cumulative probability given proportion 1/30 plus 1/15. and so on. Let's use the notation z hat to distinguish this z-score from the z-score we calculated earlier directly from the data in the sample. If we calculate the expected z-scores under the normality hypothesis for all the values in the sample, we get this table. For example, under the normality hypothesis, we would expect the first value in the sorted sample to be around 1.83 standard deviations below the mean, and the last value to be around 1.83 standard deviations above the mean. At this stage, we have two z-scores associated with each value in the sample, namely the actual z-score obtained from the data in the sample itself, and the z-score we would expect if the population from which the sample has been drawn is normal. If we now plot the actual z-scores against the theoretical expected z-scores, we get the quantile-quantile or QQ plot associated with the sample, which is shown here. If we now treat the theoretical z-score based on the position of each value in the sorted sample as a prediction of the actual z-score calculated from the data in the sample, we get an error associated with each point in the QQ plot, which is simply the difference between the coordinates of each point, as shown here. There is an error associated with the first point at index 0, an error associated with the second point at index 1, and so on. The root mean squared error, or RMSE, can be thought of as analogous to an average of these errors. The squares of the errors are used so that the signs don't cancel, and the square root is taken to return the units from squares. Notice that the denominator of n-1 has been used. This is analogous to the way we calculated the standard deviation earlier. In fact, if we compare the formulas, we can think of the standard deviation as an RMSE value obtained by using the mean of the sample as a predictive model. For the particular sample we have been using, the RMSE statistic turns out to be around 0.449. Of course, in the case that the sample rarely is drawn from a normal population, we expect the theoretical z-scores to be similar to the actual z-scores, and the RMSE statistic to thus be smaller. But without an idea of the range of RMSE values we expect if the sample is drawn from a normal population, we don't have a context in which to assess the value we obtained. For the RMSE test to be useful then, we need to have a sampling distribution of the RMSE statistic under the normality hypothesis to provide this context, which we explore next. One way to explore the RMSE values we would expect if the underlying population is normally distributed is to use Monte Carlo simulations. The way this works is, we draw a large number of random samples of the given size from a population we know to be normally distributed, and then for each sample we record the RMSE statistic value. This way we end up with a large number of RMSE values that were obtained when the normality hypothesis was true. If we do this for a sample of size 15, we get the distribution shown here. This was obtained by drawing 10,000 random samples from a normal population and calculating the associated RMSE statistic for each sample. We notice that the distribution is right-skewed, and the RMSE value we obtained from the example, which remember was 0.449, lies far to the right. It turns out that less than 1% of the simulated RMSE values were as extreme as this. In other words, we now have a p-value associated with the RMSE statistic of the sample we were investigating. The cutoff point for the most extreme 5% of the simulated RMSE values turns out to be around 0.348, also shown here. This could, for example, be used as a critical RMSE value for a test conducted at the 5% significance level. Whether we use a p-value or a critical RMSE value, it appears in this case that we could reject the hypothesis that the underlying population from which the sample was drawn is normally distributed. So we are now able to formally test the normality hypothesis using the RMSE statistic. Ideally, however, we would like to model the sampling distribution so that we don't need to rely on a large number of simulations each time we would like to perform the RMSE normality test. Fortunately, the distribution appears to be well fitted to a log-normal model. I go into the details of fitting a log-normal model to the simulated RMSE values in my paper, but here is the result for samples of size 15. The sampling distribution is snugly modeled by the log-normal distribution with parameters mu equals -1.53 and sigma equals 0.29 as shown in the slide. So now we have a formal normality test based on the RMSE statistic and a model that allows us to conveniently perform the test. The next step is to assess the performance of the test. There are two ways in which the test may err, namely by rejecting the normality hypothesis when the hypothesis is true, called a type 1 error, and by accepting the normality hypothesis when the hypothesis is false, called a type 2 error. By choosing a significance level for the test, we are effectively choosing a type 1 error rate we are willing to tolerate. For the sample we looked at earlier, we obtained a 5% critical RMSE value, for example, which effectively means we were willing to tolerate a type 1 error rate of 5%. The type 2 error rate, on the other hand, is not possible to determine a priori because it depends on the actual distribution of the population, which is unknown. The complement of the type 2 error rate is called the statistical power of the test. This is the probability that the test will correctly reject the normality hypothesis when the underlying population is not normally distributed. As a result, it is also not possible to determine the power of the test a priori. What investigators tend to do when evaluating the power of a normality test, then, is to focus on a range of given contexts, including specific non-normal populations, sample sizes, and the significance levels for testing. Once these have been specified, we can once again make use of Monte Carlo simulations, this time to evaluate the power of the test in a given context. The way this works is, we repeatedly draw random samples of the given size from the given non-normal population. For each sample, we use the test at the given significance level to accept or reject the normality hypothesis. Finally, we use the relative frequency of the correct rejections as an estimate of the statistical power of the test in the given context. In the next section, we compare the power of the RMSE test proposed here to that of existing normality tests, whose power estimates have been presented in a selection of papers over a range of contexts. Here are some of the papers I have pulled results from. Shapiro, Wilk, and Chen, and Philibin propose their own normality tests and compare the power of their tests to those of other tests in their papers over a range of sample sizes and non-normal populations. Yaziki and Yolakan and Razali and Wa do not propose their own tests, but similarly compare the power of existing tests across a range of contexts. Here are some results from Shapiro, Wilk, and Chen that show the Shapiro-Wilk test outperforming the RMSE test, whose respective results I have added on the left, for non-normal populations they describe as symmetric short-tailed. The other two tests shown are the Kolmogorov-Smirnov and Kromer von Mises tests, which generally performed worse. And here are some results from the same study for a non-normal population the authors describe as near-normal. In this context, the RMSE test appears to have similar power to the Shapiro-Wilk test, while still outperforming the Kolmogorov-Smirnov and Kromer von Mises tests. Philibin proposed a test based on the correlation coefficient of the QQ plot and compared its power to that of the D'Agostino and Shapiro-Franke tests, among others. The analogous RMSE power, which I've added on the left, appears to roughly match that of the best performing tests in each case. Yaziki and Yolakan explored the power of tests including the Jacques-Berra, chi-squared, Anderson-Darling, and modified Ugine tests. While the RMSE test, whose analogous power I've added on the left, did relatively well in some contexts not shown here, this slide shows some contexts in which the RMSE test is clearly outperformed by other tests. In my paper, I discuss why this might be the case, but we won't get into that here. Finally, a similar study by Razali and Wa, which includes explorations of the power of the Lilliefors and Anderson-Darling tests, is included in my paper. This also shows the RMSE tests, whose results, again I've added in on the left, performing relatively well against existing normality tests over a range of contexts. Overall, the RMSE test has the advantages of being based on a statistic that is easily calculated and has a simple interpretation. Further, the RMSE is naturally associated with the QQ plot, which, as I've mentioned, is already commonly used on its own as an informal visual normality test. While there are some contexts in which the RMSE test is outperformed by other normality tests, it generally performs relatively well in discriminating against non-normal populations. It tends to have least power in the cases of non-normal populations that are nearly normal. However, in many cases, this might not be a serious issue. For example, results, such as those of the t-test or ANOVA tests, based on the assumption of normality, may still hold well if the assumption is only slightly violated. In any case, the RMSE test proposed here appears to be of value, at least as an augmentation to the QQ plot when used to assess the assumption of normality. Here are the papers some of the power estimates presented here are taken from. I'd like to thank Dr. Denise Lemaire-Ronveau for her feedback and suggestions during this project. Thanks for your time and take care.